So this is GATE 2014 question number 47, which states that consider a system of 3 fermions which can occupy any of the 4 available energy states with equal probability. The entropy of the system is. So we need to find out the entropy of the system, and this is particularly a statistical mechanics based concept through which we can calculate the entropy of the system when certain particles like fermions in this case are present. So 3 fermions, 4 available energy states are there. So let's see how to proceed for this particular problem. Number 47 from GATE 2014, which states that system of 3 fermions are present, this is given, and it can occupy 4 available energy states with equal probability. This is also given, and what we need to find is the entropy of the system. Now, using statistical concept, we can show that the entropy of the system is equal to the Boltzmann constant times log of omega. S is equal to Kb log of omega. Now what is this omega? Omega is the number of possible microstates. Now what is this microstate represent? And what is another term called the macrostate? So what does macrostate and microstate represent? Just in short, so macrostate is nothing but the specification of the actual values of the parameters like n, energy. So this is the number, this is the energy. Okay. So specification of actual parameters, specification of actual parameters like this n, the number of particles, or E, the energy parameters like n, E, etc. define the macrostate of the system. Okay, but what about the microstate? It sometimes happens that in the microscopic level, if you go to the microscopic level, it sometimes happens that there are different ways. So there are different ways in which total energy of the system can be distributed. Total energy of the system can be distributed among n particles. Those different ways are called the microstates. Okay. So this is the macrostate. Macrostate means the specification of the actual parameters like n, E, sometimes volume defines the macrostate. The specification of that is the macrostate. What about the microstate? Microstate is the different ways in which the total energy of the system can be distributed among n particles. So these different ways are the microstates. So in this case, we will calculate the microstate, not the macrostate, but we can definitely tell about the macrostate. So I will give you a short example of this after this particular thing. So these are the energy states which are mentioned here, 1, 2, 3, 4. There are 4 available energy states which are mentioned in the question. So these are the 4 available energy states. Remember, we have to also remember that these are the fermions. These are also indistinguishable. At the same time, one fermion can occupy only one state, one energy state. This is the thing which is a characteristic feature of these fermions. Therefore, so one particle can occupy only one energy level. Therefore, these are the possible microstates present. That is, so 3 fermions are there. So it can be possible in the first case that it is one of the fermion is in the first state, second state there is another, third state there is another. Second possibility is that the 3 fermions are at 2, 3 and 4. Third possibility is that 1, 3 and 4, and the last possibility is that 1, 2, 4. So there are 4 possibilities in which these microstates can be found out. So there will be total 4 microstates which are present. Therefore omega, that is the number of possible microstates, that is equal to 4, which we have found out from here. Fine. Now S, the entropy, as I have said, that it is defined as Kb log omega, and people have shown it using the statistical concepts that entropy can be related to Kb log omega. So omega is 4 here. Can we write this 4 as 2 square? Yes. So Kb log 2 square, and is a property of the log of 2 square will be equal to 2 log 2. The power will come as a multiplication. So 2 Kb log 2 will be my answer. So let us see that which is the correct option. 2 Kb log 2. So B is the correct option, not the C. B is the correct option for this particular problem. So it's not C, it is the B. B is the correct option. 2 Kb log 2 is the correct option. So let us see that what is the difference between this macrostate and microstate with this very short example, particularly in case of a indistinguishable particle. Indistinguishable and suppose there are two particles present and two energy levels, epsilon 1 and epsilon 2. There are two energy levels which are present. Okay, and these two particles can occupy any energy level. So it's a kind of a boson kind of a thing, that two indistinguishable particle can be at the same energy level as well. So this is one of the criteria which I have defined. It can be anything else also. So what will happen is that in epsilon 1, suppose there is nothing, but epsilon 2 there are two particles. Epsilon 1 there is one, epsilon 2 there is another, and these are two. So these are the three possible which we call as the microstates. Okay, these are the different ways in which the total energy of the system is distributed among the two particles. So these are the microstates as per the definition. But what about the macrostate? Macrostate is that at epsilon 1 energy level there is 0 number of particles, at epsilon 2 energy level there are 2 number of particles. So this is one of the macrostate because it is giving the information about the number of particles at each energy level. Next, the second possibility, so the second thing is that you have 1 here and 1 here, and the third is that 2 and 0. So this is nothing but the macrostate. Macroscopic information is being given through these particular terms, but microscopic information is given in this. So there are 3 macrostates. So this is macrostates, not, so these are the macrostates. So there are 3 macrostates and 3 microstates in this case. But if it is a distinguishable particle, let us see one case of this distinguishable. It will be clear. So suppose A and B are the 2 particles, and again it can occupy each energy level. Means simultaneously A and B can be there at any particular energy level. So again there are 2 energy levels, suppose. So it can be possible that AB is here, there is nothing in epsilon 2. Second case, AB is here. Third case, A and B is here. Fourth case is also possible that B is here and A is here. So these are the 4 possibilities. Now if it is a distinguishable particle, there are 4 possibilities. Therefore these are the 4 microstates. Okay, these are the 4 microstates. Okay, these are the microstates. But what about the macrostate? Macrostate is the number at energy level. So there are 2 in epsilon 1, 0 in epsilon 2. In this case, 0 in epsilon 1, 2 in epsilon 2. In this case, 1 in epsilon 1, 1 in epsilon 2. This is also 1 in epsilon 1, 1 in epsilon. So these are the 3 macrostates. But these 4 microstates. So for same thing, same possibilities, you can see that for distinguishable particles there are 3 macrostates, 4 microstates, but for indistinguishable particles with same kind of a condition we have 3 macrostates and 3 microstates. So this is the general difference between the macrostate and microstate. And entropy can be defined based on the microstate, number of ways the total energy can be distributed among n particles. So omega, through omega we can use this definition Kb log omega and we can find out the answer. So in this case we have seen that B is the correct option. So for this particular question, 2 kb log 2 is the right answer. Thank you.